P, 0.953 atmospheres. So, of the two parts of the question that's regarding, this problem, we have like a stoichiometry part of the problem, and then we have an ideal gas law problem. Which part is easier for you? The ideal gas law? Once you see your information, you can plug and chug, right? But the problem is seeing the information. Like, what do you do with the very, very, very first part of the problem? Okay. I'm still assessing my progress because I want to make sure you're overly prepared for this year. What number was that? One? Oh, yeah. Okay. 1326.69 liters, sig figs. 3, so 1330 liters. All right, proceed on the next 3 while I finish checking homework. I was.
If it's a negative temperature, you subtract it.
Yeah. How's number 2 and 3? Doesn't matter, it'll work. Either way. Because the temperature and pressure are the same. Number 2, you could have converted to water moles first, or you could have solved for oxygen moles, and then converted. So either way, you're in good shape. So there's stoichiometry and gas laws in all of these. Who's on number 3? Okay, cool. Check your work with me after you get done.
For the first one, why wouldn't the significant figures be 1?
Where are you seeing 1?
Because it's 50 moles of oxygen.
It's not 50 moles, it's 50.0 moles. Huh? 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 What? What's there?
I got number 2 wrong.
Really? See what you did, Doug? Do not round in between plugging information in, because you'll have rounding error at the end if you do. If you're stuck on 3, make sure that you realize you're given octane, which is a liquid, but you have the power and the knowledge to get liquid octane over to moles of CO2 because you know how to do stoichiometry. So using your balanced chemical equation, you find these ratios. Thumbs up if you have number 3 and number 4. Okay. All right. Take 20 seconds. Sound like walk the group. And then you can come back to number 3. I'm counting my head. 20. Can you look at your evidence? No. I'm really excited on number 4, so I want to be with you. Okay, 5, 4, 3, 2, 1. Look at number 4 for me. You can come back to number 3. Number 4. If you've looked at it, raise your hand. All right, what's your thoughts, Lewis, on how to do it?
Just to do the gas law and then convert CO2 to O2 and then do the gas law.
So you're going to do 2 PVs with RTs? You're working too hard. This is the trick I showed you yesterday. Liter to liter ratios. Ready? Get ready, people. This one's a really long problem. 4.5 liters of CO2. I want you to go to liters of oxygen. Look at your ratios. What's the ratio between CO2 and oxygen?
That's going to be so short.
Huh?
That's going to be so short.
It totes is 25 moles, aka liters, so that's what you guys could do, liter ratios of oxygen for every 16 liters of CO2. 70.3 liters of oxygen. Working too hard. I almost did that too, and then I was like, oh, if temperature and pressure are the same, then you assume, in P equals RT, they would be the same doing it both times. So they end up actually canceling each other out if you do P equals RT twice. So why work that hard? You can work smarter, not harder, right? So this is a liter ratio, aka same thing as mole ratio, under constant temperature and pressure conditions. So number 4 is awesome.
Does this one work for liters?
This works for liters and moles and molecules if you are not changing like temperature and pressure conditions. Okay, so number 4 is uber easy. Okay, so I need to know right now. Gauge yourself on a scale of 1 to 10. 10 meaning I could teach this stuff, Miss Inlo. I can take your job. And 1 being I'm on the struggle bus and we're about to crash. Okay? Give me a 1 to 10. I need to know because I need to know what we're doing today. So I need to know if we're jumping lab or if we're going to do more practice. So I just need to know. I need to know. Show me your hands, people. Okay. Okay, I see at least 2 hands up for everybody, mostly. Okay, so here's what we're going to do. If you don't mind, we need time for the lab, so if we can go over the 1 through 5 from last night's homework, if we can go over that tomorrow morning, that would be wonderful. Okay, because we've done a lot of stoichiometry just through practice here. These practice questions are more like what you would see on your test, okay? There might be one where you have to find the LR and then move on. But I went ahead and balanced it for you already. So what I'd like to jump into is go ahead and teach you Dalton's Law, which is a 1 slide right here, and then we'll jump into the lab. Hi.
Hi, you have
Yeah. So Dalton's Law, 1 slide of questions, 1 slide of notes, and then we're going to do our lab, okay? And our lab will take about 50 minutes, so I just have to make sure we have enough time, so I have to scooch going over those ideal gas laws till tomorrow. Thank you for understanding. So, we know Boyle's Law. Let's see the ABCs. We know Avogadro's Law. We know Boyle's Law. We know Charles' Law. We're going to learn Dalton's Law. Darwin's Law is never like. So we're going to learn Dalton's Law. All right, it's really, really easy, people. If you have a bunch of different gases, and they're all in one big happy family together, each gas will create a certain amount of pressure. With each gas creating a certain amount of pressure, if you add up all the partial pressures, they make a total pressure. So you probably wrote this down in your reading guide 14, which I have so much paper to pass back to you, and I'll get there shortly. But total pressure is equal to partial pressure 1 plus partial pressure 2 plus partial pressure 3. Depends on how many different gases are present in the sample. So speaking of the atmosphere, what's in the atmosphere, gas-wise? Nitrogen. Oxygen.
From that side.
Uh-huh.
And the other side.
Argon. Traces of other stuff, but argon, there's a lot of argon actually. So, how many partial pressures would there be for us to get atmospheric pressure? 5. You'd have P partial pressure of nitrogen plus partial pressure of CO2 plus partial pressure of argon plus partial pressure of oxygen plus partial pressure of CO2, all equal to what's normal atmospheric pressure? 1 atmosphere. This is a sum. That's it. No multiplication, nothing crazy. That's how easy Dalton's Law is, okay? So, Dalton's Law. So in our lab, we are going to be collecting a gas over water. So do you remember drawing those silly models where you guys had to tell me which atmospheric pressure or partial pressure of the gas was larger, and I had the flask and the beaker and the graduated cylinder? Those cheesy drawings. We're doing the graduated cylinder Wednesday, the upside down graduated cylinder. So basically, whenever you have water in a beaker and you funnel gas here, there's gonna be gas up here in the graduated cylinder. It's an upside down graduated cylinder. Okay, the gas is gonna go in there in some way or form. You guys are gonna do that today. But there's water in here. Okay, the water in here vaporizes pretty easily. Meaning, when it vaporizes, it's causing a little bit of water vapor to cause gas, right? So basically, what this includes is partial pressure of a gas and partial pressure of water vapor inside of that graduated cylinder. So now we just have to consider the vaporization of water. That's it. So the total pressure will equal both of those gases together. P gas, whatever the gas is of our lab, and P of water vapor, just simply because water is vaporizing at room temperature all the time. That's Dalton's Law. Thumbs up if you know Dalton's Law. Okay. Whatever you do, though, make sure all of your gases are in the same units. Millimeters, mercury, atmospheres, whatever. That's just a kind of a given to make sure you know that. So, pull up a piece of paper. Let me tell you what to write down for your lab, because there's a couple standard pieces of information. Told you it was fast. Ready, Freddies? So, do we want to watch this video? Oh, we should probably watch the video. Why is there an eraser on here? Okay, I'm going to show you the setup. I'm going to show you the setup from a video because it's actually easier to see the manipulation. To give me about 5 minutes, but I just want to make sure you know when you see something called a mnemonic trough, that's like a bowl. Okay, it's like a little bucket, just a deep bucket. And then I'll leave this up here for later, but the Weather Channel, the American Weather Channel, publishes everything in inches. Sorry, this is the atmospheric pressure of us today. 29 inches of mercury. You can convert, okay? And then I'll pull up the water vapor pressure chart in a second. So, video. Those are materials, and you'll be massing. You have a lighter. You're going to dip the lighter in the water, and then to make sure there's a little water in all the crevices, because that'll be what's happened afterwards. Then you're going to mass the lighter. It's very specific. Put it right down the data, and then you're going to pour. This is like probably the most important part. Pour water in your upside down. The graduate cylinder. The stopper's off the bottom of it, so there's no stand on it. Okay. Pour the water all the way to the tippy top, because you want no air bubbles at the top, because that will account for some volume of gas. So you got to go all the way to the top. So she's just going to refill this to the top. Make sure there are no bubbles. If there are bubbles, oh, here's the part I have to show you. Sorry, I went too fast. You're going to take your graduate cylinder. You're going to fill it to the top, put your hand over it, and then put your hand underwater and turn it over. Invert it, and then when it's underwater, you take your hand away, the bubbles will not come back. Okay? So basically, if there are bubbles in the end, you got to redo it again. And I'll help you guys with that if you need help. After that, you're going to put a lighter underneath. Bubbles. Okay. Bubbles. You're going to put a lighter. This graduated cylinder is underwater here. It's upside down. You're going to take a lighter. It doesn't light, okay? If you click it, it's going to allow the gas to escape into the air. I'd rather not breathe that in. So you'll see right here, she just lifted the graduated cylinder a little bit and held the lighter underneath the mouth of the graduated cylinder. So when the bubbles from the lighter come out, they're being funneled into the graduated cylinder. See how that works? And then the bubbles from the graduated cylinder, from the lighter, is going to bubble up and then make a gap at the top of the graduated cylinder, because it's pushing the water out of the graduated cylinder into the bucket. So at the end, you're going to have a volume of a gas. You're going to have that lighter that you massed before and after to find the mass of that gas that you evaporated. And you'll have the pressure of the atmosphere, which is just, published online, and the temperature of the room and the water. You guys have thermometers. So basically, what formula do you have? Ideal gas law, right? And you're going to determine the identity of the gas, okay? So that's pretty much it for the setup. I just wanted to show you guys that. I'll pull up our instructions again, and let's go back to the back. You need safety glasses, not goggles, okay? Alright, start reading. Get the party started. Stop the class there. No bubbles. You will have to do the math on it. I'll be back.
And the video from today, is it already?
Getting ready to stop it right now and post on